Okay, so this is experimental communication. It's week 3, and this is about playing with code. Now, just remember my background. I come from a fine art background. I'm a painter. I've never been taught programming or computer or any of that at all, not even my MA. And so I'm not naturally somebody that you would think of as a coder, but in actual fact, you will find that it's not as painful as you might think, and weirdly enough, it's actually quite fun. And when you see what it can do, you go, oh, and you realise that you can do it. So this is I'm just going to run through some thoughts about code to start with. So first thing to know is that there are things called programming languages, a range of different ones, and there are high level and low level. So high level are ones which are closer to English, so whereas low level is just a series of symbols and dots and asterisks. But high level, it's changed, so it's almost becomes English, so it's more readable. The problem with high and low level languages is that high level languages, in order for them to be human readable, they have to go through quite a lot of processing in order to get them so that you can read them. Low-level languages talk straight to the computer, and it's up to the human to interpret what's going on. And obviously that has an overhead. So games machines, which is all about performance, they write their code direct in low-level languages, so C++, that sort of thing. So if we talk about artists and designers, artists and designers have always been interested in the sorts of things that programming can do. They've been interested in things like algorithms. So an algorithm is a set of instructions that you put something in, it processes it, and then something else predictable comes out the end. So the algorithm would be just a set of instructions. So if you said to me, if I got you all to give me a piece of paper and my instructions were to scribble on it in red marker, then rip it into the smallest tiny pieces and give it back to you, I could give it back to you. But you could give me anything, I would still scribble on it, cut it into tiny pieces and give it back to you. Okay, so the algorithm is the set of instructions. It doesn't matter what comes in and what comes in gets processed. The algorithm is the set of instructions. So just as an example, this is a game board found in a grave from 2600 BC, and it's to do with patterns and algorithms. So these are a set of instructions that led to these patterns being drawn on this box. This is an Aztec stone, again very, very driven by the algorithm. It's very rotate a certain amount, draw the same thing again, rotate it a certain amount, draw the same thing again, and in terms of colour as well. Even things like this is Southern India, 1970s. There's a set of rules, a set of instructions that have led to this image. All of these lines have been drawn with reference to a set of instructions that have led to how they've come out. Even things like this is Tibetan monks making a temporary sand mandala. Don't sneeze. This is a set of instructions that led to this looking like it is. Okay, very, very ordered, very careful. Move around a little bit more, do the same thing again. Move it around a little bit more, do the same thing again. So this is somebody that you ought to know who she is, not least because she's a very important and significant person, but also because of the room, the building that we do our course in normally. I know some of you are in Lithuania, but this is somebody called Ada Lovelace, and she's the daughter of Lord Byron and his wife Lady Byron. And obviously Lady Byron is what the building is named. It's because Lady Byron originally set up a school on the site of where UWL is now. But this is their daughter, Ada Lovelace. I think about 1815 or something. She died quite young, so I think she died 1850s, 1860s, something like that. She's a very, very significant person in the history of computing. and not always recognised for that. She did a lot of work on something called the Charles Babbage. It's known as Charles Babbage's the difference engine in the computing machine, which you can see in the Science Museum. Well worth going to see. Amazing thing. It was so sophisticated that he made a machine that was in effect the first computer, and yet they didn't have the technology at the time to physically make it. It was a mechanical computer, and Charles Babbage and Ada Lovelace worked on it together, and she was absolutely central. Great mathematician, great pioneer of computing, and obviously because she's female, she was never recognised at the time, and so the computer became known as Babbage's difference engine, but in actual fact it was as much her as anybody else. So a very, very significant person. Interesting the link to UWL as well. This is somebody called another female important person in computing, Commodore Grace M. Hopper. She was working for the US Navy around the time of sort of Pearl Harbor, that sort of time, and her notable achievement was she was looking after these computers that were not quite, there was something going wrong with it. They'd come in and it was huge rooms full of these spinning disks and something not quite working. And she would go into the room and she discovered that a little moth had got into it and had stopped some of the mechanics functioning properly. And she called it a bug. And it was a bug in the first computer. So she was the one responsible for naming the idea of a software bug, and it came from a moth being embedded in the mechanics of early computers. This is the difference engine. So it's Charles Babbage and Ada Lovelace. This is the thing that we were talking about. Couldn't do very much. You could just add and multiply and subtract. But at the time, amazing. All Babbage and Ada Lovelace designed this thing. They could never build it because they didn't have the kinds of technologies available to them that they could make this from. It was only later, about I think the 1980s, that this thing was actually built according to Babbage and Ada Lovelace's, Babbage's design, but Ada Lovelace was key in the planning of it. And it was only then that we had the technology able to build it, and of course it worked perfectly. Very important. I've just put here a list of interesting people I think you should have a look at. There's a whole lot of people, really significant computer artists, designers. I'll make this available as a list on the site as well. I recommend that you have a look at as many of these as you can bear, really. There's some on there that are my absolute favourites, like a sort of a third of the way down, somebody called Manfred Moore, really brilliant artist, designer, great ideas. Joshua Davis, we're going to have a look at in a minute. Carsten Schmidt towards the bottom. Really lot of interesting, Golan Levin, really interesting people you should look at because they're quite inspirational, even though what they're doing is immensely sophisticated and beyond what I'm going to be able to teach you in 1 or 2 weeks. Okay. But let's just move on and look at Joshua Davis. So Joshua Davis really working now, started life working with Flash, which you remember, you may still know. Obviously it's the route that most people are getting their computers infected nowadays, but alongside Flash, which was really a simple animation software, what it had was a programming language. It was called ActionScript, and it was very powerful. And Joshua Davis was one of the early adopters of ActionScript, and he became one of those sort of gods of ActionScript and Flash. Did amazing things with it. But when Flash began to die, and when it did die, and as you know, Flash is, I don't think there's anything that Adobe make that still, maybe they make something called Flash Animator, and then make the Flash player to keep things running. But Flash has died, and Joshua Davis jumped ship, and what he jumped to was something called processing, which we'll get to in a second. If we just have a look at some of his work. So this is Joshua Davis's website. You should definitely go and have a look at this. I've probably shown it to you before, but let's just pick up any of these. To start with, they're great still images, but the point about these is they're actually motion. So here's just doing interesting things with text. So these are algorithms that's driving this, a set of rules to decide what's drawn on screen. And he's writing this with code. If we look at some of the other things, so that was obviously motion. I think this one is a motion piece too. Again, it's just a series of instructions that lead to these sorts of images. I don't know how you would achieve these images without writing code. Very, very difficult to understand how you do it without. If we just had a look at, and obviously some of this looks, it's music. Lots of this stuff is used in music videos and all sorts of installations. But equally, in terms of graphics, here's the UEFA Champions League opening visuals. Very much a graphic design piece. You'll see it used in graphic design context. See the Pepsi links.
One kiss is all it takes. Falling in love with me. Possibilities. Take the night out love real easy. Something in you.
Okay, so you get the idea. Print stuff, moth bodies. I'll just skip and show a few more. This, very typically him, these sorts of colours. Okay, so go and have a look at these on your own, but they're fantastically inspiring, and they're all written with code. Okay, next person just want to have a look at is Carsten Schmidt. So if we just quickly head back and look at Carsten Schmidt. Okay, so let's just have a look at Carsten Schmidt. This is a piece from 2007, but he's very much active now. Just want to show you this. So this is the branding for an arts festival called Love Bites that used to happen every couple of years in Sheffield. Sadly doesn't run anymore. But you can see on the right that the images, he designed this little monster, these monsters. They're all generatively produced on the fly with code. He wrote the rules. He didn't actually design any of them himself. He just literally put together the rules that generated them. So I'll just play this little video so you get a sense of what it's about. So because there's no actual plates involved in the printing, there's nothing to stop every single ticket, every single poster being different with a different monster on. So that's what he did. He just wrote the rules, and the whole branding was based around these characters. And these are them. Thousands of them. What's interesting is he also generated names. I'll just read you this little piece from him. Since we wanted to create true characters, we needed to define and assign another important parameter to each monster: names. Each name is generated using a few very basic rules. This is the algorithm that I was talking about, sometimes resulting in hilarious outcomes and unexpectedly suitable names. Our basic rule of naming is consonant, vowel, consonant, plus a few more extra rules as filters applied on top, e.g. not every letter but both vowels and consonants can be doubled up. There's a usage limit for every letter per name. Monsters do have gender. Female names end with an A or an I. Males are ignorant about that aspect. Letter Q is always followed by a U, etc., etc. These are just extra rules to help tailor things to make it work more effectively. And these are the things they ended up with. So every ticket, every poster was a different character, which is fantastic. It's a great branding project. Okay, that's Carsten Schmidt. So let's talk now just a bit about processing. So processing.org. Processing.org, I will just take you to now. So processing.org. So processing is a programming language which is specifically designed around the visual arts. Okay, it's a flexible software sketchbook and language for learning how to code within the context of the visual arts. Since 2001, processing has promoted software literacy within the visual arts and visual literacy with technology. There are tens of thousands of students, artists, designers, researchers and processors and hobbyists who use processing for learning and prototyping. Okay, so this is literally, it is aimed at you. The good news is it's free, incredibly well documented, lots of books about it. There's lots of tutorials. This guy at the top, Daniel Schiffman, does really good stuff, easy to follow, quite entertaining. But obviously I'm the most entertaining, so I'll be getting you started with this. I think you're getting a bit cool. Should we make it a bit warmer? Let's make me a bit warmer, shall we? That's not warmer. There we go. Is that warmer? A bit warmer, maybe. Oh yeah, that's better. A bit brighter. That's not. Oh, that's warm. That's a bit brighter. Okay, so processing is free. Download. Really straightforward to use. There isn't a lot to it. I will show it to you in a second and we'll just get started. But it's an amazing piece of software, very powerful, and hopefully you'll get a sense of it from when the exercises once we start doing it. So with that in mind, let me just show you processing. So processing was written by two initially PhD students, Casey Reese and Ben Fry, and they were students at MIT and Massachusetts Institute of Technology, and it was their a project which they did as their, I think it was their, maybe even their PhD piece, but it became adopted worldwide, lots of people doing it, and even there are spin-off pieces to it like Arduino, which is using the sum of the lessons of processing to control hardware. There's a little hardware board which I can show you. So this is a piece done with processing. So let's have a look at the MIT So in this case, it's an identity that can change. It was designed to move. It was designed to produce different options, but still within the same set of rules. So it still looks like the same identity, but what it meant was that you could generate endless, thousands of different possibilities within the set of rules that they had. So if we just have a look at some more. So here they are. You can see they're all very much the same identity. Here it is used on business cards, websites, t-shirts, bags, all sorts. Every member of staff had a different image on their card. and it's all generated with the code. Okay, so processing, really a great piece of software. Let's just, before we get any further, let's just quickly be sure that we understand what I mean by writing code. In the end, computers are just lots of switches. Each switch is called a bit, and each switch can only ever be on or off, hence 1 or 0. So I've prepared a little video for you. Okay, a bit of GCSE maths now, looking at binary. So when people talk about 8-bit computers, they were talking about 8 switches. So every number could be represented by 8 switches. Because you can't record a 3 because computers can only record 1 and 0. So to record 3, you would have to turn on a certain number of switches. Okay, so with everything set to 0. Obviously you've got 0. If you put 1 here, in other words, if it's on, then you've got 1. To get to 2, you'd put this one to 0 and this one to 1. Then to get to 3, this would be 1 and 1. In other words, on and on. To get to 4, you would put 1, 0, 0. So this is 0, this is the 0 and 1. This is up to 2. This is the 4 column. And then to get 5, it would be 1, 0, 1. 6 would be 1, 1, 0. 7 would be 1, 1, 1. 8 would be, you then switch to this column, so it'd be 0, 0, 0, and so on. Okay, so let's just delete all of that. So this column is worth 2. This is a 1 in there represents 2. In other words, if this is on, it's 2. This one is 4. This one is 8, and you probably recognize these numbers now. 16, 32, 64, and 128. Okay, so if you wanted to write 128, you would put 1, 0, 0, 0, 0, 0, 0, 0. Okay, so 129 would be 1, no, 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 1. Now, if you put a 1, 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 a 1 in there, it actually adds up to 255. Plus the 0 state, that gives you, the next one would trigger it, would be to 256. But in effect, 8-bit computing gives you 256 colours, 256 numbers. Okay, that's my whiteboard writing with a mouse. So 8-bit gives you 256 numbers, and hence 256 colours. You will also notice that in Photoshop you can have 256 levels of red, 256 levels of green, and 256 levels of blue. 8 and 8 and 8, 24. So standard 24-bit computing. You then later see 32-bit computing with more information, but you get the idea. So that's how binary works, and that explains 8-bit. Okay, so it's just switches on or off, 1 or 0. So processing. Let's get started with it. Okay.